Welcome back, everyone. In this video, I'll be continuing the section on areas and distances. Where we left off, we were talking about the velocity, and in the previous problem, we related the velocity. We found the area under the curve of a pretty straightforward one because it was just a rectangle. And we talked about how finding the area under the curve of velocity gives us the distance traveled, which is pretty much the position with some minor adjustments. But for now, we'll just think about it. And what's going to be helpful going forward is thinking about it when we find the area under the curve, it's related to the antiderivative because the position is the antiderivative of velocity. Okay. Now I just want to do another one of these distance problems, but where this is a more realistic type of situation where you would actually do these area approximations to calculate something because you don't actually have a function, you just have a table of values. So this one says the speed of a runner increased steadily during the first 3 seconds of a race, and her speed at half-second intervals is given in the table below. We want to find the upper and lower estimates for the distance traveled during these 3 seconds. Right. So there's no way of us knowing the actual distance traveled because we would need the speed she is traveling or velocity she's traveling at every single possible time. So a continuous y equals f of x function, we don't have that. So we're going to just have to use this table. But what's happening is if your speed or your derivative related to whatever you're talking about is increasing or decreasing, and it's not changing, so it's not going up and down, it's just increasing or just decreasing, then what happens is when you do the left endpoint and right endpoint estimations, what you end up getting is one of them is going to be the upper bound, one's going to be the lower bound of the estimate. Okay, so you will need this constant increasing or constant decreasing for these upper and lower estimates to make sense. Which one is it going to be? You can actually draw the picture to figure out whether the left or right will be the upper or lower. But since we've got to do both anyway, you can just do both and then figure out from there with the bigger one is the upper bound, the smaller one is the lower bound. All right, so what I'm going to do here is just point out a couple things. We have half-second intervals. What I'm going to do very, very roughly is just kind of sketch what this is going to look like so we can relate it to our rectangles. So we have time at 0, time at 0.5, time at 1.0, 1.5, 2.0, 2.5, and 3.0. And I'll draw the picture for the right endpoints. Since we've seen both quite a bit, we really know what's happening. Now, what we're looking at here is from time 0 to time 0.5 would be rectangle 1. I'll just abbreviate that R subscript 1. Time from 0.5 to 1 will represent the base of rectangle 2. And then we'll pretty much keep going on. So starting at 1 to 1.5, this will represent rectangle 3. From 1.5 to 2 will represent rectangle 4. From 2 to 2.5 will represent rectangle 5. And then finally from 2.5 to 3 will represent rectangle 6. Now this sort of relates back to our b minus a over n because what's happening here is all the time intervals are evenly spaced out. So really the base of the rectangle, the b minus a over n, is the 0.5. All right, so just remember that. And the way we draw it on here, this is exactly b minus a over n because it's going to represent all of the rectangles. Now, if I go ahead and just draw in the right ones, we don't have a curve here, but think about what x values am I going to use, or t values for time am I going to use to draw my right ones? Well, at rectangle 1, I'm going to use 0.5, and that has a velocity of 5.7. So let's just pretend that's right there. And once again, this is the picture for the right rectangles. So that's rectangle 1 for the right one. And then for rectangle 2, the base is here. We'll use time as 1.0 and the speed is 11.2. And this probably is not going to be drawn to scale, just kind of illustrating what we're doing here. And the distance traveled would be this rectangle. The rectangle 3, the biggest t-value is 1.5. The rightmost t-value is 1.5, and the speed is 14.1. So let's just pretend that's right here. And you probably get the idea. I can do the other 3 as well. So with rectangle 4, we use time equals 2 because that's the right one here, and that's going to be 18.8. So I'm not going to really clearly label it. And then the next one would be 19.8, a little bit higher. And then finally at 3.0, 20. Now keep in mind that if we did the left ones, then we would just start at t equals 0, then t equals 0.5 for rectangle 2. So we kind of have the same idea here. All right, so the right endpoint estimate, well, our formula is always b minus a over n, which is our 0.5 times, and then we want to add up all the velocities. So v at time 1 plus v at time 2. And then we have 6 of these, and I don't want to write down up to t6. So v at time 6. But as we just illustrated, and we could probably do this from the chart if we're more comfortable with it now, is t1 is 0.5, t2 is 1.0, t3 is 1.5, and so on. So we got, this is 0.5 as we already described up here. And then the first velocity we're using is 5.7 because we're using t is 0.5, its velocity is 5.7. Second velocity is 11.2. And you're pretty much just going to add all these up because time rectangle 3, we're using 1.5, which is 14.1 for velocity. At rectangle 4, we're using this time, which has 18.8 velocity. At rectangle 5, we're using this time, which is 19.8. And then the third one, 20. Or sorry, I would keep wanting to look at the number here, but the sixth one, time is 3, the velocity is 20. Now, these, just because these are kind of messy, I'm going to go ahead and just add all these up in the calculator. So we got 0.5. And you can do this the other way, add up all the function values, which is what's inside here, and then multiply by b minus a over n. But because it's kind of spelled out in a table for me, I just write down the whole thing in these type of problems. 5.7 plus 11.2 plus 14.1 plus 18.8 plus 19.8 plus 20. And we get 44.8. So this is the right endpoint estimate. At this point, we don't necessarily know if it's the upper or lower, so I'm just going to keep it as the right for now, but it's 44.8. And what are the units here? Well, the speed is in feet per second, and the time length is in seconds. So when you multiply the units, you get feet per second times seconds, and the seconds cancel, so it's 44.8 feet. But that should make sense because we're talking about distance here. There would be no time with it. All right, now the left estimate. What's the difference here? Well, the b minus a over n is fine. So I'm going to just start. We know it's the same formula here. It's just the t values are slightly off. So b minus a over n is 0.5. But now when we plug in t values, or we're looking at velocity values, we're looking at the left. So for R1, we're going to look at the left t value for R1, and that would be 0, and the velocity is 0. And we're pretty much just going to take the left one. So the first 6 here for R2, the t values range from 0.5 to 1. The left one is 0.5, and we use 5.7. And hopefully you can see the next one will be 11.2, 14.1, 18.8, and 19.8. Now, one thing you can kind of do with these left and right ones, especially for tables, is the right ones, they're pretty much going to always start at the first one, because this is going to be the left of the first one, this is going to be the right of the first one, and it's going to go all the way down. When you're looking at the left endpoints, you start at the very first one and you go all the way down until the second to last one, and you stop there because this is going to be the right endpoint of the last one. It's not a left endpoint of anything. But if we go ahead and add all this together, Really, the only difference is this 20 is being replaced with a 0, and 20 times 0.5 is 10. So you can do this in the calculator, but I know this is going to be exactly 10 less. So it's 34.8 feet. And now at this point, you may have realized that when we were filling out the formula, but this number is bigger. So this is the upper estimate. And this number is smaller, so this is the lower estimate. So as long as she is increasing her speed the entire time, meaning at like 1.7, she's still between 14.1 and 18.8 and not like above or below, just out of that range, we can be guaranteed that this runner, just based on this data points, ran between 34.8 and 44.8 feet. And that's much more useful than taking a function itself with a name and then estimating the area. However, what we're going to see is that when we want to find the exact areas or distances, when you have a function like y equals x squared, you're going to have to set up one of these left or right estimates. It's not going to matter which one. That's a very useful thing. But then you have to do the limit. All right. And for this, I had a little picture here from a website that I think explains it a lot more. But to really explain the background real quickly, it says to find the exact area from the approximated area. The idea is to not use a set number of rectangles, but instead you write your formula using n rectangles. All right, so in this one we had 6. In a previous example, I believe we did 4. In the starting example of the section, we had 3. But you don't want to specify how many rectangles you have. You want to say there are n of them. And the reason is we actually want to think about what happens as the number of rectangles goes to infinity. And the way we talk about infinity properly involves calculus. That's doing the limit. So we write our formula using n rectangles. Then you take the limit as n goes to infinity. And what happens is the number of rectangles will get greater and greater, and it'll actually quote unquote converge to the exact area. So what converge means is just basically if you draw the picture out and you draw more and more rectangles out, it's going to fit perfectly under the curve. It's going to match the area. And there's actually a pretty useful website here. I'm going to bring it over just to visualize this. A very useful animation. I just Googled something called a Riemann Sum because this is what they could be called. And I'll go ahead and write that down as well. But this is a nice little animation. For this one, I have f of x equals x squared. So it's actually what we're going to be working in the problem from x equals 0 to 1. So a is 0 and b is 1. That's exactly the exact area we want to find in our problem. And we want the exact area. So this is the left endpoint. It's not going to matter if it's left or right. So I'm going to stress that this is just a left endpoint approximation picture with n equals 4, the number of rectangles. Now I'm going to increase that number to 8, so double it. And the idea is if you notice the area that's missing, so we're underestimating here because there's this white space underneath the curve that our rectangles aren't hitting. And if I go to 16, it's going to become less and less area. And if you're not seeing that quite yet, what you can do is make this number 100 really big, and you pretty much can't even see the white areas. You'd have to scroll in and see that it's barely off. And then if you did 1,000, it might not even, oh, it can do that. It actually fills it in because the rectangles are so small. Right. But the idea is you're not actually perfectly there until you do the limit as n goes to infinity. So that's what we have to really arrange here. Now, one thing I want to stress by doing a problem like this isn't how we're going to need to find area going forward. It's sort of like the definition of the derivative, the limit definition. It gives you an appreciation for all the formulas we're going to have going forward. All right, so the idea is this, and we're going to speak this with this in generality. And these are called Riemann sums. Now, if you don't remember or know that name, you're not going to be grilled on it, so it's okay. But it's just going to be the formula that we've been dealing with here, the area approximation formula. It doesn't matter if you use left or right. And the sum here is from I equals 1 to n. We're going to have b minus a over n. Okay, and then we're going to multiply it by the function value. So remember the function value, we kind of, in our formula, let me scroll back up here, use this xi or xi star because it just depends on what it is. We're going to just leave that b for a second, f of xi star. And once again, the star is optional, so if you don't like the star there, you don't have to include it. Just reminding you that some books will probably use that if you look in other places. Okay. But the whole point of the Riemann sum is now this is the area approximation for n rectangles because we're starting from 1 to n, and we want to do the limit as n goes to infinity. So what's happening here, we know how to do limits going to infinity. We usually deal with x, but we can do it in. What the hard part usually is of this problem is simplifying, finding a formula for the inside and doing it. And one thing that's going to be very new here when we do these problems is that since n is right here, you cannot bring the limit inside this summation formula. So this is very important. You cannot bring the limit inside the summation or the sigma. And once again, if you didn't watch the preliminary video, make sure you watch that on the sigma notation so you know what I mean. But we cannot bring this inside because there's an n in there, and if we bring it inside, we're kind of skipping doing this in. Okay, so what we're going to go ahead and do, usually to be nice, we'll start with 0 here, and actually we'll pretty much do just 0 to 1 for the most part. But when you start with 0, it's easier to write the formula with the left endpoints because it doesn't matter which one you choose. So we're going to do left endpoints. And now one thing I'm going to go ahead and warn you of is figuring out this xi is probably the hardest part. And if you choose right endpoints, your answer at the end will be the same, but your xi's will be slightly different. So in order to do this, what you want to do is visualize your a to b interval here, starting at 0 and going to 1. And I'm going to draw a couple with n specified just to really make it make sense. So let's pretend this is the picture with n equals 3. Then I cut it into 3 equal pieces. And we know this is going to be 1/3 and this is going to be 2/3. And that makes our 3 equal intervals, 1/3, 2, and then length of 1/3, length of 1/3. And we're not going to write them down, but if we are doing left endpoints, then we would use x equals 0, x equals 1/3, and x equals 2/3. All right, now what if we go up to n equals 4? So we're still starting at 0 and going up to 1. But I want to use n equals 4 just to see the pattern here. Well, I'm going to cut it into 4 pieces now. And now each one is going to be 1/4 wide because I'm doing from 0 to 1 in 4 equal pieces. So this is 1/4, this is 2/4, which I'm just going to leave as 2/4, and 3/4. And if we did the left endpoints, what are we doing? We're doing 0, 1/4, 2/4, and 3/4. Right? And we want n equals 4, so we want to plug in 4 numbers. But like I mentioned in the previous problem, whenever you're doing left endpoints, you pretty much always start with the leftmost point, which is 0, and then you go up until the second to last one, and that'll give you your x values. All right, so what happens if we don't specify n? Well, we can't really draw a picture, but let's do our best. What you want to notice here is that this first one, we're starting at 0 for the left endpoint. It doesn't matter which one, as long as really we're starting at this a value, but for us, a is 0, and that's really helpful. So we're going to be starting at 0. And now what you want to notice about the second one we're plugging in, we had 1/3, and then we had 1/4. Well, in general, we're plugging in 1 over n, because n equals 3 and n equals 4. Right? So we've got 1 over n there, and we're going to plug that in. And then what is the next one? Well, at n equals 3, the third one we plugged in was 2 over 3, and then we plugged in 2 over 4 for n equals 4. Well, that's just 2 over n. So we've got another point with 2 over n, and we'll plug that in. And once again, we're not specifying in here, so I'm just going to write down one more for emphasis. We can see what we're plugging in at n equals 4 here, which is 3 over 4. That's really 3 over n. Okay. All right, so what's actually happening here? What is the formula for xi? And remember, this is for left endpoints. So like I said, doesn't matter which one you do, just choose left endpoints. Well, we're increasing by 1 over n every time, but really that's b minus a over n. And what we want to do is we're starting at we're starting at 0. So what's happening here is we're starting at, if we think about multiplying this by I, if we start at I equals 0, what's happening? Well, we're plugging in I equals 0, and this whole thing is 0 because it's a 0 times something. It doesn't really matter what it is. Then at I equals 1, actually, let me go ahead and just rearrange this a little bit. So this is going to be our formula for plugging in for xi for the left endpoint. When I equals 0, if we're starting at 0, it's just 0. If we're plugging in I equals 1, what is it? Well, it's 1 times b minus a over n. And that's exactly what 1 over n is in this problem because b and a are 1 and 0. If you plug in I equals 2 to your formula here, you get 2 times b minus a over n. And then that's 2 times 1 over n, which is 2 over n. And this is going to work forever. All right, now if you do the right endpoints, so it's up to you which one you're going to plug in. One thing I'll point out here is that you start at I equals 1, so you have to make an adjustment when you do the left endpoints because we want to start at I equals 0. So for the right endpoints, it's a little bit easier to actually write down the formula and use this, but it's easier to explain with the left endpoints at the beginning. So the formula is actually exactly the same. It is still xi equals I times b minus a over n. What's the difference here? The only difference is when we do the right endpoints, so I can highlight these in red, we would start here, here, and here, 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 and here, and here. We're always starting where I equals 1. And we go up to what? So right endpoints start at I equals 1. Why does that make sense? Well, this is where I equals 1, and we kind of went over that, so we're starting there. And it ends at I equals n. Oops, I equals n. So how do I know it ends at I equals n? Well, if I go ahead and plug in n here for our formula, we get n times b minus a over n. Those cancel out, and I get b minus a. Well, what's happening here? What is b minus a? B minus a is 1. Now, if your starting a value is not 0, you have to make one more adjustment, and this is where it kind of gets annoying. This is why starting at 0 is so great. So we're going to say, we're going to use this formula because it just matches up. In our formula, we're starting at I equals 1 and going to n, so it matches up with our right one a little bit better. And this is if a equals 0. If a does not equal 0, then you have to make a minor adjustment. And this is why we pretty much, when we do this, only start at a equals 0, is you just have to add a on at the end. Because what happens is what if a is 1 and b is 2 for this formula? Well, we would end up at 2 because we want to end up at b, but b minus a would be 2 minus 1, which is 1. So just keep that in mind in case you ever come across or are reading some literature about this and you want to know why is that plus a there? Well, really it's because a is not 0. Right. So I think even though we're in the middle of this problem, it's good to just stop here because this is really the hard part. But once you have this formula down, you never have to try to reuse it again or try to redevelop it again. Okay, so what you should have taken so far from here is that you should use right endpoints when you're doing these Riemann sums. And this is a formula for our xi if a equals 0. This is a formula for our xi if a does not equal 0. So what we're going to do in the next section, actually plug in a and b into our formula here along with what our function is, which is x squared, and then actually do this sum. So I will see you there.